Welcome back everyone. In this lecture I will continue with the definition of group action, and we will also see some examples of group actions. Okay, so let us recall what we defined. So, I gave two definition of group action. So, we will always work with the first definition. Okay. So, what what is the meaning of a group G acting on this set X? So, again we take set to be non-empty set. Okay. So, we say, so recall, this is the recap. So, we say G is acting on the set X again via this tau. If the tau, there is this tau is a group homomorphism from G to Sx. Okay. So, we use this shorthand notation. So, what is this shorthand notation that I introduced? So, this is to denote the image of x under tau g. Okay. So, here we have g, let us say it is mapped to tau g. So, then the shorthand notation is indeed for x in x and g in g, you denote tau g of x by just g dot x. Okay. This is the notation that we will be using. So, this notation, like I said, should not be confused with the group multiplication, because this G is coming from capital G and this X is coming from capital X. So, this is from the group and another element from the set. So, let us see what this means. Okay, in terms of this shorthand notation, what is the meaning of tau being group homomorphism. So, recall again, so some of the things that we proved. So, if you take identity of the group and then if you act it on this capital X, like I said, it should be just mapped to the identity element via this tau should be mapped to the identity element in Sx, which is nothing but identity map from x to x. So, this identity element acting on some element small x in capital X should be x, and that is true for all capital X, sorry, all x in x. So, then if you take these two elements G1, G2, and then if you want to act that on x, so then you see that you can apply first G2 and then you can apply G1. So, that is the meaning of this tau G1 G2 is same as being tau G1 tau G2. So, what is tau G1 G2 of x? So, that is supposed to be tau G1 of tau G2 of x. Okay. So, if you write using this shorthand notation, you can see that this is G2 dot x and then this is G1 dot x. So, which is same as G1 G2 dot x. Okay. So, that is what I have written here and here. This is the identity. So, the identity mapped by tau is identity of x. So, Eg dot x, which is tau identity of x, is just x. Okay. So, now if you think about it, tau G inverse will be tau G inverse. So, in particularly, so you have this G inverse acting on this x, that you can just simply tell that okay, we do not need any notation for that actually, but you should remember that tau G inverse should be tau G of inverse. Okay. So, the G inverse will be given by the inverse of G only. Okay. That is what. So, we say that okay, the given element G in G acting on given element x in x via this G dot x. Okay. So, that is the meaning of this thing. And of course, we are suppressing the notation, we are hiding actually this tau under the carpet, okay, but sometimes it is very useful. Okay. So, one should get used to this shortcut notation, then it becomes like somewhat easier to do the computation or proving. Okay. So, let us start looking at some examples. Okay. So, now as we actually define, okay. So, if you start with any set x, so let us call this is example 1, you take any x, let us say this is a non-empty set. So, then you have this Sx, so which is the group of symmetric group on x, okay, the symmetric group on x. So, what we can do, we can take any subgroup of this Sx itself, then that will actually naturally octant x. Okay. So, you take any subgroup of Sx, for example, you can take Sx itself, then you have this inclusion from G to Sx. So, let us call it iota. So, this inclusion is a group homomorphism. Okay. This is obviously a group homomorphism. So, in particularly you can get action of this G on X via this inclusion. Okay. How it is acting? Okay, given G in G. So, this G is already a map from X to X. So, then this X map to G of X. So, that is your G dot X. You can verify easily this is a group homomorphism because it is just an inclusion of G inside Sx. So, that in particularly gives you the action of G on capital X via this inclusion. Now, if you take G to be Sx, it will be just a natural, okay, naturally the Sx will act on X. Okay, this is one example which will be used later when we restrict to X being finite set 1 to n. Okay. For example, one can prove that given any permutation on 1 to n will have what is called cycle decomposition using this action. Okay. So, we will be interested in Sn, which is okay, the symmetric group on this 1 to n, okay, and we will say that Sn acts on this 1 to n, and we will use this to actually conclude something about elements of Sn. Okay. So, this will be used again. So, here is the example 2, we can actually have various action of group on itself. Okay. So, let us start with G being a group. Okay. So, then G acts on G itself via what is called multiplication. Okay. So, I did not actually really differentiated between the right action, left action and so on, but from the notation it is clear that okay, once I define group action using this homomorphisms. So, then it is clear that okay, it is just only the matter of notation. So, if I write this image of tau G of x as G dot x, then we are talking about the group acting on capital X via left, okay, the G dot x. So, this is a way of writing G dot x. So, because we are writing the group elements on the left, we call this is left action. Suppose if we write this as x dot G, okay, so then this is naturally will be right action. So, one can talk about left action and right action. Let us not get into those things. So, you can see that there is a dictionary between left action and right action. So, we will only stick with the left action. We will always use this notation because I introduced the group action via this group homomorphism. So, we do not care about this left and right actions. We will just take always use this G dot x to denote tau G of x image. Okay. So, now why I was actually telling about this, because when I say G is acting on G via multiplication, there are two ways to multiply. One can multiply by left as well as by right. Okay. So, then because I am only interested in the left, so we will actually talk about this left multiplication. Okay. What is the meaning of this? So, let us see. So, given this group element, okay, so we want to define a map from SG. Okay. So, how one can define this? Let us see. So, let us call this is tau again. So, given G, we want to define tau G, and the tau G is given by what is called this left multiplication. So, what is tau G here? Tau G is a map from G to G. So, maybe I will call it because it is a left multiplication, I will rename this, maybe I will call it capital L. So, this is the left multiplication. So, how LG acts? LG of some x is given by just Gx. Okay, it is a usual multiplication of group elements. Okay. So, indeed if you use that dot notation, G dot x is exactly Gx. So, let us not get confused with this group multiplication and this group action, abstract group action. So, because of that I will just use LG whenever the multiplication is mentioned or this particular map is mentioned. Okay. So, LG of x is just given by Gx. So, now the question is why this LG is an element of the symmetric group, that is something we need to verify. Okay. So, that is indeed obvious, because the inverse of LG will be LG inverse. Okay. So, let us verify LG is indeed inside SG. Okay. So, for that what we need to verify, LG is a bijective map. So, you can see that LG of, okay, suppose Gx equal to Gy, okay, let us say it is injective, LG of x equal to LG of y. So, then that would imply that Gx equal to Gy, but by multiplying G inverse on both sides, you can see that this implies x equal to y. So, indeed LG is injective, that is obvious. Now, given y, what you can do? You can take G inverse y, and then LG of G inverse y is going to be y. So, that proves that it is indeed surjective. So, that means LG is indeed inside your symmetric group SG. So, now why this association is group homomorphism? Why this is group homomorphism? So, you compose them. Okay, let us take LG1, LG2 of x. So, then what it is? It is G1, G2 x. Okay. But this you can write it as G1 times G2 x. Okay. So, that means you first apply LG2 on x and then you apply LG1 on this LG2 x. Okay. So, this is what indeed this says. So, LG1 G2 is exactly LG1 composition LG2. Okay. So, it is indeed group homomorphism. So, that means this G is acting on G via left multiplication or via this map L. Okay. So, here is another interesting action, okay, which is very important action. So, this is the example 3. So, again the group is acting on G via what is called conjugation. Okay, this is a conjugate action, group acting on itself via conjugation, okay, or conjugative action. So, what is the meaning of that? So, let us see. So, what one can do, okay, let us first of all look at the map that we are interested in. You fix some G in G. Okay. So, then using this G, what one can do? One can define this map CG which is a map from G to G. What it does, okay, because we have group in a group multiplication, we can also give an element, okay, of given two elements G and X, we can talk about the conjugate of X by G. Okay. So, that is the map we are interested in. So, you take given X, you look at Gx G inverse. So, that is your map Cg. Okay. So, we want to say that the Cg is again bijective map from G to G. So, why it is a bijective map? Let us verify. Suppose Gx G inverse is equal to Gy G inverse, that means the two images are same. So, then by cancelling G and then G inverse, you can see that X must be equal to Y. So, this proves that Cg is injective. Okay. Now, if you take any Y here on the left side, you can take G inverse Yg, and naturally it will be mapped to Y. Okay. So, that means Cg is surjective. So, that what we indeed proved that Cg is inside Sg. Okay. So, now one can use this to define this conjugation action. So, define a map from, let us call it C only, G to Sg, where G goes to this Cg. Okay. We need to verify this map is indeed group homomorphism. Okay. Let's see what it does. So, G1 G2 on X is going to be G1 G2 X G1 G2 inverse. But if you work it out, this is exactly same as G1 of G2x G2 inverse of G1 inverse. Okay, because this will be switching. See, G1 G2 inverse is G2 inverse G1. So, then if you think about it, this is exactly equal to, first you apply Cg2 on X, okay, that is the middle term. Okay, this term is same as this term. So, then you apply Cg1 on this term. Okay. So, then you are getting your Cg1 G2 of X. So, this proves that Cg1 G2 is same as Cg1 composition Cg2. Okay. So, that implies this C is a group homomorphism. Okay. So, that means we can actually define this group action via the conjugation. So, this is very interesting action. Again, these actions will be used in order to conclude many interesting facts about our group, as well as the important things that are involved in this. Okay. So, as before, the example 4 is going to be just the thing that you have seen in linear algebra. Suppose if you start with the group G, which is a subgroup of, let us say, GL of some vector space or the Euclidean space, whatever you can fix. So, let us say V is a vector space over, let us say, some field F. Okay. So, then naturally G is acting on this capital V. Okay. How it acts? Because GL of V is indeed sits inside SV. Okay. The natural inclusion is going to give you group homomorphism. Okay. Because GL of V is nothing but the set of all invertible linear maps. Invertible linear maps means they are all bijective maps. Okay. So, similar to this, one can actually take, okay, anything like, for example, one can take G to be, okay, let's use some different notation. Let us say H being a group, okay, given group. So, then one can look at this automorphism of H. So, these are all group isomorphism from H to H. Naturally, this is sitting inside SH. Okay. So, now if you take any subgroup of this automorphism of H, then naturally this G also acts on this H via this inclusion, okay, because G sits inside SH is going to give you group homomorphism from G to SH. So, one can take some subgroup of automorphism of H, it naturally act on H. Okay. So, all these actions are very interesting, okay, they are very useful. So, let us see so I want to actually give you another important action. Okay. So, let us call it example 6. So, this is something related to subgroup. So, you start with the group G and then take H being a subgroup of G. Okay. So, this is a subgroup. Then we can form this G modulo H, which is the set of all left cosets of H in G. So, what it is those X H where X in G. Okay. So, now what we can do, I can take X to be this and then I can define a natural action of G on this X. What is that? So, let us call it again, this is also some kind of left multiplication, let us call it LH. What is LH? LH of some G is a map from X to X, okay, given by some coset XH map to GXH. Okay. I can naturally multiply by left of all these left cosets, again I will get left coset. Okay. So, that is the map that I am actually associating with LG of H. Okay. So, now let us check this is indeed group homomorphism. First of all, why this LHG is inside SX. So, this is defined from X to X given by okay, X capital H map to GX capital H. So, maybe I will use G modulo H here just to emphasize it is acting on this G modulo H. So, now note that suppose you have okay. So, we want to say that this thing is actually really really bijective map. So, one can is simply check. So, the LHG inverse is the inverse map. Okay. So, this is not very hard. So, let us verify it is actually satisfying the group law. So, then it becomes clear this is actually the inverse map. So, LH of G1 G2 is applied on any H XH is going to be G1 G2 XH, but this can be grouped as follows. So, that means this is exactly equal to first you take LG2 apply it on XH and then you apply LG1 on this. Okay. That tells you that LH of G1 G2 is same as LG1H LG2H. So, that proves that this map is indeed group homomorphism from G to SX, okay, and this indeed defines action. So, this action again is very important action, okay. This again we will use later, okay. So, G naturally acts on not only on G, it is naturally acting on all the left cosets of G. Again you can define the right action on the right cosets, let us not get into that, maybe this is enough. Okay, so I end with one final example, which is again uses subgroup. So this is now so here we used the left multiplication on the left cosets. So similar to this, we can use the conjugation on all possible conjugates of H. Okay, so here is the example 7. So let's take G to be a group and H being a subgroup of G. So what one can do, one can look at all possible conjugates of this H via all the elements of G. Okay. So this is just all possible conjugates. So this I want to take as my set X, and then I want to define the action of G on this capital X, okay, via just conjugation again. Okay. So then G acts on this XX, let us call it this is conjugation on this capital H. Okay. Then you map CH G, which is a map from X to X, where CGH of some element, okay, which will look like H. Okay. Okay, maybe let us use X. X H X inverse, you just conjugate via G. So G X H X inverse G inverse. So which is exactly equal to G X H G X inverse. Okay. So now I want you to verify this is actually a group action. Okay. So I will leave it to you to check CH G inverse is the inverse map of CGH. This is something you can verify. Now what's about the group law? So the group law is if you take G1 G2 H and apply it on XH X inverse, you get G1 G2 XH X inverse and then G1 G2 inverse. Okay. But if you rewrite this, you can see that, so this thing, okay, if you rewrite, you get G1 G2 applied on XH X inverse, G2 inverse, G1 inverse, which is same as saying you apply first CG2H on XH X inverse, okay, and then apply CG1 on that. So that means CG1 G2H is same as CG1H CG2H. So the group laws are indeed satisfied. So that means this actually gives you action of this capital G on this set of all conjugates of this subgroup H. So note that so this is a simple exercise. So any conjugate will be a subgroup, because one can look at this inner automorphism corresponding to G, where X mapping to GX G inverse. So that we have verified that is actually an automorphism. So image of capital H will be just a GH inverse. So that will be a subgroup inside G. Okay. So basically you are collecting all possible conjugates of H, which are all subgroups, and then we are saying that G is indeed acting on this this collection of these subgroups which are conjugate to H. Okay, so we have seen many examples. Okay, I urge you to actually kind of go through this very carefully, because so group action is very powerful tool. Once you abstract things, okay, so now you have so many examples for which you can apply and then directly get consequences, okay, or applications. Okay, so I urge you to actually go through this very carefully before actually attending the next class. Okay, I'll stop here and we will actually continue with some properties of group actions and some terminologies related to group actions in the next class. Thank you. I'll stop here.